56 meters tall, 2,000 tons heavy, 2.5 million individual parts. And yet, it only flew for 30 years. Today, I'll show you what really made the Space Shuttle work. Welcome to Tech Behind the Legends. I'm Ivan Claps. Over the next 16 minutes, we'll witness a complete launch together and see how every single system actually worked. Stay with me. This is going to get intense. This is STS, the Space Transportation System. NASA wanted a reusable spacecraft. What they got was a machine pushed to the absolute limits of what was technically possible. 3 components: the orbiter, carrying the astronauts; the external tank, the largest thermos flask humanity has ever built; and 2 solid rocket boosters that, once ignited, could not be shut down. In just a few minutes, this colossus will lift off. But before that happens, let's take a look at what's really inside. Let's take it apart and see what we're dealing with. 3 main assemblies. Each one on its own would be an engineering masterpiece. Together, they form the most complex flight system ever built. The orbiter is the actual spacecraft, 37 meters long, wingspan of 23 meters. It carries the crew, the payload, and 3 of the most powerful rocket engines in the world. The orbiter is made up of 7 main assemblies. Up front, the crew module. In the middle, the payload bay, nearly 18 meters long, almost 5 meters in diameter. This is where satellites flew, where the Hubble telescope was carried, where entire ISS modules were delivered. At the back, the 3 main engines. Then the wings for landing, the vertical tail, and on either side, the 2 OMS pods for orbital maneuvers. Every part has exactly one job and absolutely no backup. The external tank, 47 meters tall, 8.5 meters in diameter. On the outside, that famous orange-brown spray-on foam insulation, just 2.5 centimeters thick. That's all it took to keep what's inside cold. Up top, 630,000 liters of liquid oxygen at minus 183 degrees. Down below, 1.7 million liters of hydrogen at minus 253. That's colder than the surface of the moon at night. The solid rocket boosters, each one 45 meters long, packed with 503 tons of solid propellant. APCP, ammonium perchlorate composite. Once it's burning, you can't stop it. There is no shut-off valve. Inside, the propellant is shaped into a star pattern. That makes sure the burning surface grows evenly and the thrust stays constant. The connections between segments, the field joints, were completely redesigned after the Challenger disaster. T-minus 30 seconds. The sound suppression system kicks in. Over the next few seconds, more than 1 million liters of water will be pumped underneath the stack, not for cooling, but to dampen the acoustic energy that would otherwise tear the boosters apart. T-minus 10, 9, 8, T-minus 6.6 seconds. The 3 main engines fire up in a precise sequence, each one 120 milliseconds apart. That's not random. That timing prevents the vibrations from amplifying each other. Watch the stack tip forward, 60 centimeters. This twang is intentional. The engines push the stack sideways first, then it springs back into perfect vertical position. That's exactly when the boosters fire. But what exactly happens inside one of these engines? Let's take a look. The RS-25, also known as the Space Shuttle main engine, 2.2 meganewtons of thrust per engine. At the heart sits the combustion chamber. Inside, the temperature reaches 3,300 degrees Celsius. The pressure, 220 bar. That's hotter than the melting point of iron. And yet, the chamber holds because it's actively cooled. 1,080 thin cooling tubes wrap around the chamber. Liquid hydrogen flows through them at minus 250 degrees. Inferno on the inside, cryogenic cold on the outside. Only millimeters of wall between them. The turbopumps are the real miracle. They spin at 35,000 revolutions per minute. That's almost 600 times every second. They move 500 kilograms of fuel every second. T0, the boosters fire. In a fraction of a second, total thrust jumps to 30 meganewtons. That's the power of 140 Concorde engines running simultaneously. The stack climbs at 3.2 meters per second squared. Within 10 seconds, it's already 100 meters high. Within 1 minute, it's 12 kilometers up. And that's just the beginning. Let's take a closer look at how these boosters actually work. Each SRB is essentially a massive solid rocket, 45 meters long, 4 segments, 1,300 tons of propellant. But the real secret lies in the geometry.
The solid fuel isn't a solid block. There's a star-shaped cavity running through the middle. When combustion starts, it burns from the inside out. This shape keeps the burning surface constant for the first 50 seconds, which keeps the thrust constant. At the bottom sits the nozzle. It can swivel up to 8 degrees. That's thrust vector control. 2 hydraulic actuators move the entire nozzle. That's how the whole stack steers itself before aerodynamics even kick in. 7 seconds after launch, the roll maneuver begins. The stack rotates around its own axis to align with the correct flight path. This movement was programmed into the onboard computers before launch, calculated down to the second. After 1 minute, the stack is already 12 kilometers up and approaching Mach 1. But now comes the most critical phase, Max Q. Max Q, the point of maximum aerodynamic pressure. The stack is now faster than the speed of sound, but the atmosphere is still dense enough to put massive stress on the structure. Wrong timing here, and the stack tears itself apart. The solution? Throttle the main engines down to 65%. Less thrust, less aerodynamic load. As soon as the atmosphere thins out, it's back to 104%. But at some point, the orbiter has to come home. And during re-entry, the temperature on the belly reaches 1,650 degrees Celsius. No metal survives that. NASA's solution was revolutionary and incredibly fragile. 24,000 tiles on the belly, 7,000 on the upper surfaces. Every single one is unique, handcrafted, numbered, installed in a very specific position. Each tile is 90% air, trapped inside silica fibers. On the nose and the leading edges of the wings, even that's not enough. The heat there is even more extreme. That's where RCC comes in, reinforced carbon-carbon. The same material that failed when Columbia broke apart in 2003, after a piece of foam from the tank punched a hole in it. 2 minutes and 5 seconds after launch,
The boosters are burned out, but they're still firmly attached to the tank. Now, pyrotechnic explosive bolts fire, and at the same moment, 16 small separation motors ignite. Both boosters drift cleanly away from the stack. They'll fall into the ocean under parachutes, get recovered, and be refurbished for the next mission. The rest continues on alone, orbiter and external tank. But how exactly does this separation work? Each booster is connected to the external tank by 4 struts. Inside each strut sits a pyrotechnic explosive bolt, a bolt with a built-in charge. At separation, all 8 bolts, 4 per booster, fire within milliseconds, simultaneously. At the same instant, 16 small separation rocket motors ignite, 8 per booster, 4 at the front, 4 at the back. Those motors burn for just 830 milliseconds. But that's enough to push the boosters safely away from the stack. If the timing isn't perfect, they collide with the external tank, and the mission is over. Climbing at 145 kilometers per hour, the stack pushes higher. The atmosphere up here is so thin that the engines can run at full power again, 104%. They're burning nearly 1.5 tons of fuel every second. Look at this. 8 minutes after launch, we're already past the Kármán line, the official edge of space. But we still don't have enough speed for orbit. While the engines run, let's look inside. From the LOX tank up top, liquid oxygen flows down through a 17-inch feed line to the orbiter. That's a pipe with a 44-centimeter diameter. 300 liters rush through it every second. At the same time, liquid hydrogen flows from the lower tank. Both propellants meet inside the 3 main engines. The mixture ratio is exactly 6:1. 6 parts oxygen to 1 part hydrogen. More hydrogen than you'd think is needed because the excess hydrogen actually cools the combustion chambers. The connection between the ET and the orbiter is a marvel. These disconnects can seal completely shut in a fraction of a second, the moment the tank separates. Otherwise, tons of fuel would pour into the orbiter. T plus 8 minutes 30 seconds. MECO, main engine cutoff. The main engines shut down. After 8 minutes of constant thrust, suddenly, silence. The stack is now flying through space at 28,000 kilometers per hour. That's 7.8 kilometers every second. At this speed, the shuttle circles the Earth every 9 minutes. 18 seconds after MECO, the external tank separates. Explosive bolts fire. The orbiter pitches its nose slightly down, and the tank drifts away upward. The ET is the only component that doesn't come back. It cools into the artwork and burns up over the Indian Ocean. In orbit, different systems take over now. The 2 OMS pods at the back, Orbital Maneuvering System. 2 engines, each with 26,700 newtons of thrust. They run on hypergoals, fuels that ignite on contact, no spark needed. For fine attitude corrections, there are 44 additional RCS thrusters, reaction control system, distributed across the nose, the aft pods, and the OMS sections. They can rotate and shift the orbiter in any direction. 6 degrees of freedom, 3 translations, 3 rotations. With nothing but short impulses, the orbiter can align itself more precisely than any other spacecraft. Each thruster pulses in millisecond bursts, sometimes hundreds of times per maneuver. 400 kilometers up, low Earth orbit, 28,000 kilometers per hour. The orbiter is now in a safe flight state and ready to begin its mission. The first thing that happens, the payload bay doors open. On their inner surface are radiator panels that radiate the orbiter's heat out into space. Without them, the shuttle would overheat within hours. The Canadarm, officially the Remote Manipulator System, 15.2 meters long, 6 joints, designed and built in Canada. It was the first true robotic arm ever used in space. Each joint is driven by 2 motors, one as a backup. The rotation gets reduced through what are called harmonic drives by a factor of 50. That's where the arm gets its incredible precision. It can hold a position to within 2 millimeters, in a vacuum, carrying 30 tons. At the end sits the end effector. 3 thin wires close around a grapple fixture on the satellite, like a lasso. That's how satellites were caught, repaired, and released again. Hubble was serviced 5 times with this arm. Up here, everything that makes the shuttle complicated just disappears. Up here, there's only silence. 16 times a day, the crew sees a sunrise. Every time, it's different. Every time, it's overwhelming. 135 missions, 355 people sent to space, over 500 million kilometers traveled in orbit. The Space Shuttle program was the most ambitious spaceflight effort in history. But there were losses too. Challenger in 1986, Columbia in 2003. 14 astronauts never came back. Their names should never be forgotten. The Space Shuttle is a museum piece today, but its story lives on in every astronaut flying to the ISS, in every new rocket that gets reused. If you enjoyed this film, hit subscribe. There's more coming on tech behind the legends. Until next time, even.